So look, this is not difficult. There's nothing difficult, but watch this. So the new kind of question might be, can you find dy? Okay, now I'm standing right in front of it. Sorry.
Yeah.
But can you find dy? Well, there it is. I mean,
10x dx.
and so the way you find dy is you take this derivative now, and you instead of calling it dy dx or dy over dx, when you take this derivative of y, you could kind of call it dy. And then you take the derivative, which is 10x, but then at the end it spits out a little dx.
Yeah.
I mean, that's what this says. This is I'm defining the differential dy. I didn't explain it that great, except I said it. I mean, it's almost nothing to explain. It's just kind of this notational thing. It's like a new notation. I mean, before today, what would I have said? Take the derivative, and you would have wrote y prime is 10x, right, you guys?
Right.
But another name for y prime is dy dx is 10x. It's the same thing. And then maybe you can think, if you don't mind, please think about multiplying the dx to the other side. And then you've got what I'm trying to explain here. And then you have, okay, so that's it. And we'll use that a lot in Chapter 5, actually. We'll use that kind of a lot in Chapter 5. But what they do in 4.8, we can use this for some cool little word problems about error. So I can adapt this and use this idea. So watch this. This is pretty cool. Look, I'm going to have to draw this picture. You ready? I'm going to have to do this. So I've got a function. All right, I've got an x value. When you plug x into the function, it has a y value. What do you call it? F of x. You plug x into the function, there's its y value. Okay. You move x over a little bit. In other words, you add a little delta x, and you get this new place. You call this new place x plus delta x. You guys okay? I've talked like this before. You plug it in the function, you get a different y value. What do you call this y value? F of x plus delta x, right? All right, cool. Now, if you actually subtracted those two y values, you know what you'd have? If you subtracted those two y values, you'd have what's called the actual change in y. The actual change in y. Right, this y minus this y. Okay. If I subtracted these two x's, I'd have this change in x. You know, that's what this is here. That you're adding. You're adding your change in x to this, but if you subtracted them, you'd have this change in x. Okay. Now hang on. That's that. That's that. That's that. That's that. So again, the change in y is right here, right, you guys? Between those, just the change in y between two y values on a function. I mean, how many? All right. Now, the derivative. So when you take the derivative, you get dy dx. Dy dx is the slope of the tangent line. So then you might have a tangent line right here. Sorry. Look at this. Look at this. Look at this. Look at this. All right. So now you have a tangent line right here. And then here's what we do. We call that delta x. We call it the same thing as dx. And when you plug x into the tangent line, doesn't it, it's the same point as it is on the function, right? That's why it's tangent at that point. So, but when you take this new x and plug it into the tangent line, look, you've got this y value. See this? This change in y is called dy. This change in y is called delta y. So what the hell am I saying? I'm saying delta y is the actual change in y on the function, which we all do anyway. And I'm saying dy is the change in y on the tangent line. which is not the function. But for very small, listen now, for very small changes in x, the tangent line practically is the function. Maybe you don't like that. Practically is. I mean, it's not. But look, right? But that's the idea. The tangent line and the function are god dang close, dude. For teeny little changes in x, they're practically the same damn thing. I mean, my exaggerated picture out here makes it, does dy look like it's the same as delta y? No, and they're not the same. But for very small changes in x, they're closer and closer to being the same. The tangent line is a good approximation for the function. Therefore, what they do is they say that dy is a close approximation for delta y. And then we use that idea. Let me see, how am I going to use that idea? dy is f prime of x dx. What is delta y according to this picture? According to that picture. What is delta y? Good. F of x plus delta x minus f of x. Good, good, good. If I add this over here, I get f of x plus f prime of x dx is f of x plus delta x. I think I can use this in some cool word problems. Let me try to use this in a cool word problem. You ready? Not really a word problem, in this approximation problem. Watch this. I want to know the square root of 52. Okay, watch this. I want to know the square root of 52. And, well, when we got to pretend your calculators are broken. Pretend like there was a solar flare came by or something. Whatever. Actually, first I'd like to pretend your calculator is not broken. Tell me what this is. What is the square root of 52?
7.2.
Okay, I need a bunch of decimals. 7 point.
2, 1, 1, 1, 0, 2, 5, 5, 1.
2, 5, 1. All right, thank you very much. So pretend we don't know that, but I want, well, I do. Pretend we don't know that. But that's the square root of 52 according to your calculator? Okay, thank you. All right, what I want to do is try to get an approximation for that. Pretend I don't know that. I want to try to do the square root of 52 without a calculator. How the hell am I going to do this? I'm going to do this. So first of all, we need a function. I think my function should be the square root of x. Okay? That's all right. Now I need an x and a delta x. To get to 52, I want to pick an x. I want to pick a nice square root. So I think I want x to be 49 and delta x to be 3. Then wouldn't this be 49 plus 3? Wouldn't this be 52? Wouldn't this be the square root of 52? Okay. Good. So that's the right-hand side of that equation. The left-hand side is this. I need f of x plus f prime of x dx. Now wait a minute. Did I just call these equal? Hold on. When I started this up here, weren't they approximate?
They're about, yeah.
This is approximate. This is an approximation. We're doing an approximation here. All right, here I go. Here I go. I'm going to need this. I need the function evaluated at x. I think that's the square root of 49. Plus, I need the derivative of that function evaluated at x. Anybody know the derivative of this function?
1/2 x, 2 negative 1/2.
To the negative 1/2. 1/2 x to the negative 1/2. He's right. And then if I clean that up, that's 1 over 2 square roots of x. That's what that is. What am I plugging in for x?
3?
No.
Oh, 49.
For x, I'm plugging in 49. and then it's multiplied by, hang on, look, this f prime of x is multiplied by dx. And what's dx? Over here, what was dx?
The delta.
It's the delta x. It's the same thing. Is delta y the same as dy? No. They're close approximations. Is delta dx and delta x the same? Yeah, we treat them the same. Treating them the same. So my dx in this formula is a 3. Dude, this should be it. This would be a good approximation for f of x plus delta x, or the square root of 52. Let's see if it is. You ready? What is this, a 7? What is this? 7 times 2, 14. This is 3/14. Oh, so this is 7 3/14. So 7 3/14 is a good approximation for the square root of 52. That was tricky, wasn't it? Now, are we good? Is it good? What is 7 3/14? Help me, please. What is 7 3/14?
7.2142857
All right. Well, 21428. This is 21. All right. Well, whatever. Not too bad. It would have been better for a smaller delta x, but with this problem, I couldn't really do a smaller delta x. That's a good problem. I like that problem. I'm using differentials. I'm using the dy, the fact that it's a right. Let's do another problem. The other place these differentials are used is for error problems. And we call the little dy and the little dx the error. Okay, let me try one of these. In 4.8, let me try this. There's this problem number 30, and it says the measurement of the radius of a circle is 16 inches. Okay, write that down. The radius is 16 inches. That's what it measured to be. The radius of a circle is 16 inches. But there was a little error involved when I measured it. Hang on, what did it say? There's a possible error of 1/4 of an inch. You know what I want to call the error? The measured value is r. The little error I want to call dr. That's the little error in measuring the radius. What was it? 1/4 of an inch. All right, let's see what they ask. Use differentials to approximate the possible propagated error in computing the area of the square. Oops, it's not a square. Circle. All right, I need the area of the circle. All right, you guys, what's the area of a circle? You know the formula? Pi r squared. All right, if this is my r, can you plug it in and tell me the area? Sure. Pi times 16 squared. Everybody knows that's 256 pi. Anyway, that's just measuring the area. They wanted to know because there was error in measuring the radius, then there's going to be error, propagated error, in measuring the area. It's hard to say all these words. The error in the area is what I want. The error in the area, which, by the way, I'm going to call that this. dA is the error in measuring the area. So I want a formula for dA. Well, I got a formula for A. How do you get a formula for dA? Take the derivative? Take the derivative.
Would be
The derivative of A is a new thing. I'm calling it dA. I guess I could call it the derivative with respect to R. I could say that, but I'm not going to say that. I'm going to say the derivative of A is dA. The derivative of the other side is 2 pi R dr. This is kind of this new way of doing a derivative with differentials. Are you guys all right? Sort of? All right, listen. Now the question is, what's the error in measuring the area? That's this thing. And do I have enough information? I've got the radius was 16, and the error in the radius was 1/4. This is the error in measuring the area, is what this is. What is it? 8 pi. Somebody tell me what that is. 25.13 square inches. That's the error in measuring the area. Error gets compounded. I'll tell you what. Let's forget calculus for a second. Let's do this. So, without any error, you ready? Okay, back to this. Without any error, what was the actual area? Okay, thank you. All right? You got a radius, you got an area. No big deal. You got a radius, you got an area. Now, what if we had this error? Let's see what would happen. What if the radius was actually 16 1/4? So then it would be pi times 16.25 squared. You guys following me? I'm adding that error into my radius, and now I'm going to calculate the area. How much is it going to be off? What is 16.25 squared? Times pi. Go ahead, I'll tell you what, multiply that by, give me a big decimal for all this.
Okay. Let's see.
Just give me an answer. 829.6. Tell me this one. What's this answer? 804.2. So here's the measured area without any error in the radius. If you add the error to the radius, here's your new area. What's the difference? This would sort of be the actual change in y right here. This is the actual change in y. We approximated the actual change in y by doing what's called a differential. We came up with this approximation for the error. We're going to call it our error. But you can calculate the actual error by doing this. What's the difference here if you subtract those? 25.4. Holy shit.
Yeah.
Shit. Excuse me. I mean, is that good? What did I say?
Yeah.
So dy approximates delta y. Remember the picture I had up here? The actual change in y is not the same as dy, but it's a close approximation for small changes in x. And I just did that. The actual change in y for this area is this. The approximation for the change in y is this. And it's darn good. You know, is that a lot of error?
Depends on what you're measuring.
Yeah, I know. I'm measuring the radius of this circle, and I'm calculating the area of this circle. I mean, the radius only had a 1/4 inch. It was 16 inches, and it only had a 1/4 inch of error, which wasn't much. This kind of feels like this is a lot of error. I'm saying, is it a lot of error? I'm sort of being rhetorical, because the way you calculate if it's a lot of error or not is you compare it to the measured value of A, what you do is you do dA over A. And you can call this relative error. Let's check this out. I mean, that's the error. But if I do dA over A, it's called the relative error. It's 25.13 over the actual measured A. What's the actual measured A? The first one, not the one with the error, the first one. 804.2. Now listen, please divide that for me. What is this?
0.031.
Wow, thank you. 0.031. If you multiply by 100, you move the decimal over a couple places, and you get 3.1%. And you can call this a percentage error. I don't know what kind of science classes you guys have had, but when you're in lab and when you're doing science, oftentimes you're measuring and you calculate errors and you calculate percentage errors, and maybe you do it kind of like this, but well, you probably don't do this calculus.
No, we don't.
But you might do this here at the end. You take your error and divide by the measured value. Right, that's a percentage error. Right. It's called, well, I called it a relative error. When you multiply by 100, you call it a percentage error. To me, it's practically the same thing. You just make it a percent. Anyway, now that I know it's 3.1%, I kind of think, yeah, good. It's not that much error. Whatever, 3% error. It's not 10 or 20% error.
So what was the point in doing, taking the difference of these two areas, the 829 and 804?
What was my point? I felt like over here what I was doing was an actual change in the area.
Okay.
Not using calculus. Just measure the area with the 16, okay? Measure the area with the 16 1/4 and see what the difference is. That's the actual change in the area.
Okay.
But in these problems, we're not asked to actually calculate that. We're asked to use the differential. Use the differential to approximate the error. So we do it like this. And it's a good approximation for that answer.
Do we have to do like a plus or minus one for?
That's sort of true. I didn't see the plus or minus in the problem, but you're sort of right. This could be plus or minus 1/4. You could throw a plus and minus right
Then you have a range.
here, right. The error could be plus or minus. It depends on the problem. Sometimes it's specifically plus or specifically minus, and it's not plus or minus. You got to watch how it's worded. Well, you guys want me to quit today? All right, I tried to introduce this last section. In a way, it's not hard, but it's got a lot of funny uses, and maybe you didn't pick up on all that. I did some good problems here. I'll try to help you Wednesday. I'll help you with your take-home quiz, your actual quiz, maybe some 4.9 stuff. Or 4.8, I mean, 4.8.
4.7, 4.8.
Yeah, maybe 4.8. Yeah, might be a question. Yeah. 4.7 was good, and that's, yeah. 4.8 didn't make your take-home quiz, so this is kind of new. Right. There is no 4.9. Sorry, I misspoke.